Basically now we got rid probably of the most difficult part of today's lecture. The rest is more, a scientific description of some technical aspects, not requiring you to basically use any advanced method. Now, I conclude my talk about the cut-off catalyst layer, presenting you something about the reduction, the real kinetics of the oxygen reduction reaction. As you know, this reaction is extremely complex, I guess, as you may expect. This reaction is extremely complex and goes through a quite complex reaction mechanism that is still not known, even though platinum is extremely studied and probably is the most studied material ever in electrochemistry. If you do not know what to use, you use platinum generally. Now, here just to show you what are the implications of the use of platinum in fuel cells in automotive operation. Even though there are many aspects that we should consider, the most relevant one is the fact that when you operate your fuel cell at high potential, so let's say above 0.8 volt, there still is a relevant potential for fuel cell operation, especially in automotive. What happens is that your platinum surface, consider this as your platinum surface being these small spheres as platinum atoms, you would expect it to be basically free and to have oxygen arriving on top of it and then very fast reacting, producing water, consuming one ion, four ions, 4 electrons, and so on. Actually, at high potential, what happens is that platinum forms a very strong bond with oxygen, with the oxygen atom, a single atom, covering the platinum surface. So what happens is that some oxygen gets trapped or sticked on this surface, and basically the platinum linked to this atom will not be available for the electrochemical reaction. For sure, this is an easy way to tell this story, because platinum oxides are a family of phosphor oxides. You can have just one single atom of oxygen, you can have 2 oxygen atoms, you can have OH, so oxygen plus hydrogen, and you could have oxygen also moving in the bulk of the material, so it's an extremely tough topic. Nevertheless, the concept remains the same. So when you go at high potential, part of your platinum surface will be blocked by these oxides. The result is that your kinetics that should behave as a single Tafel law, so as a line, as a straight line in your Tafel plot. I don't know if you had a chance to solve this kind of plot. Let's review it. Maybe I just zoom on it. So, this is a so-called Tafel plot. In this case, you are plotting the electrode potential as a function of the current in a logarithmic scale. Okay? According to Tafel law, you should have your kinetics just lying on a single line, this dashed line, for example. You know, well, the Tafel slope will be exactly the slope of this line, exactly, isn't it? And the activity of your catalyst, the I star, will just shift up and down your curve. This is something you will get confident with maybe when we will introduce the model, the fuel cell model next lecture. But nevertheless, the point is that for a very simple Tafel law, in this plot you should have all your potential data placed on a single straight line because of this logarithmic behavior that has the electrode potential versus the reaction rate or the current density. Okay? And instead, what happens in reality is that you deviate from this law, and increasing the potential, what happens is that a large fraction of your platinum is actually covered by oxides and it is totally blocked, making, in practice, this means that less platinum is available for the electrochemical reaction. So it means that you're expected to draw a certain current at a given potential, but instead, in real world, you have a lower current, because it's like having less platinum in your system. Okay? Okay. So, this phenomenon is very important when you try to fit your experimental data above 0.8 volts, where you see a large deviation between the theoretical taper slope and the real electrokinetics. There are some simple laws, but if we look at the formulation of the reaction rate, this is affecting the parameter SV, that is the surface available of the catalyst. Okay, this SV is how much platinum you have in your electrode, is a square meter of platinum proportional to cubic meter of the electrode. So it means that the real surface of your catalyst, and we will put a star to remember this, will be lower compared to the one geometrical that you have in your system. You can measure this with some experimental techniques, and there are some correlations available. What you observe is that compared to the maximum available platinum surface that you could have, when you increase the potential, you are decreasing the available surface. And this decrease becomes relevant above 0.8 volt. Okay. Obviously, this occurs because the oxide is forming some kind of bond with the platinum that depends on how charged is the platinum itself. So how much is this potential difference? That's why the coverage or the effective surface free changes with the potential, because the potential determines how strong the oxide is sticked to the catalyst surface, basically. Okay. Then, basically, we have the situation where at high potential we have oxide coverage, and so we have platinum blocked by oxides, and instead at low potential we get rid of oxides and we observe a single taper kinetics that we can actually use to fit our kinetic model and to get relevant parameters for the oxygen reduction reaction.
Excuse me?
Yes?
Can you just repeat that part, like the potential?
Okay, see, this is the point. Regarding this, you say that SV star is the effective surface that is available, considering the part of it is blocked by oxide. And SV max is the maximum free available surface that you could have. So when you see, in real world, from experimental information, you see that by increasing the potential above 0.8, this surface goes far below 50%. This means that above 0.8 volt, you start to observe a deviation between the theoretical and the real kinetics. The fact that this effect is dependent on the potential of the electrode resides on the interaction, the electrochemical interaction between the oxide and the platinum atom. Okay. Now, we are done with the cathode catalyst layer. That actually took us a lot of time because it's a very relevant component in fuel cells, because in there we have a lot of platinum, it is costly, it tends to have a strong degradation. Instead, we go now to the polymer membrane. As we did before, we try to recover our knowledge about how we treated the membrane in our lumped model. And if you remember, we said, okay, in the lumped model we will consider this ohmic loss over the membrane as a linear contribution, proportional to the ionic resistance of the membrane. Okay, but what happens in the real world is that this is not true anymore, because the conductivity of the membrane, as you saw during last lecture, strongly depends on the water content, on how much water you have in your membrane, and so, for example, the relative humidity of the gases that you are feeding in your system. So this means that if we move from this lumped model and we consider the ionic conductivity no more as a simple constant, you will find that you have to carefully study how water is managed inside your fuel cells. Because depending on your operating condition, you may have a lot of water, and so a very good membrane conductivity, or you could have very little water, and so very low membrane conductivity. Okay? So, water effects on electrolyte resistance is the major deviation from our lumped model to the real world. Okay. There are some minor effects, additional effects. First of all, the fact that the membrane is not perfectly insulating your gases. Okay, so you can have that some oxygen can permeate through the membrane and go from the cathode to the anode. Also, some hydrogen can permeate from the anode, cross the membrane, and go on the other side. These effects that we will not discuss in real world are important when you are considering the fuel economy. So you have to consider that your consumption of hydrogen will be slightly higher because of hydrogen going into the membrane and going in the cathode. But the very important phenomenon is the water transport across the membrane. So actually, even though gases can permeate in very low amounts across the membrane, so oxygen, hydrogen, nitrogen will hardly, in very limited amount, go through the membrane, water instead has a massive permeation across the membrane. Because water can dissolve inside the membrane and gets transported across the membrane according to several very complex phenomena that are the electroosmotic drag and the diffusion that were introduced actually last lecture. So when you want to study a membrane, what you have to do is to care a lot about how much water is inside your membrane, basically. I don't know if you already have been told about this. There are several polymers that constitute the membrane. All of them are patented and can be produced only by selected industries. The most famous one is the Nepion, that is a brand from Chemours, produced in DuPont. Another famous one is the Aquivion, that is the ionomer from Solvay. All of them have the characteristic to show this functional group on the side chain of the polymer. In fact, all of them are composed of two major parts. The so-called backbone, so the horizontal part, that gives the mechanical strength of the membrane. So this part is necessary in order to have a lot of pressure difference on the two sides of the membrane and avoid a leakage or a hole making inside of the membrane. Then, on this backbone, another branch is obtained from chemical processes. And this secondary branch is very relevant because on top of it we have a functional group that contains sulfurs that is called the sulfonic acid that has an acid behavior. And actually this is the real responsible for ion transport inside your membrane. Because this thing that looks much like an acid can form this hydrogen bond and so have from one chain to the next one that can transport this hydrogen along a very long chain, as for example you could expect to happen in sulfuric acid, for example. In sulfuric acid you have this proton hopping from one side to the other and so freely moving inside of your membrane phase. For sure, there are other famous polymers. So, what we care now for is the water content inside the membrane. So, we said the more water we have, the more conductive is our membrane. And this is measured by a parameter that is generally indicated as lambda, that is called the water content, and is the ratio between the water molecules divided these sulfonic groups, the moles of these sulfonic groups that you have in your membrane. So, water content of tens means that per each sulfonic group I have 10 water molecules. Okay? If I try to picture this, you will see in here this black line is the backbone of the polymer, and this black dot is the SO3- group. So, for example, at low water content, it will mean that we'll have just few water molecules around your polymer. And then if you increase the water content, the water molecules, the white ones, will become more important. And typically that's what happens between water content between 2 and 14. Okay. If you go even higher, so if you have the possibility to introduce a lot of water inside your membrane, that's what happens when your membrane is in contact with the liquid water. What happens in this case, you have a single liquid water phase forming inside these channels that are present inside of your polymer. Okay, so the water content is the ratio between how much water I have per sulfonic group in my membrane. The higher the water content, the higher the water I have inside my membrane. Okay. In the next slide, you have a kind of physical visualization of this. So imagine that this is your polymer, basically, in two different cases. One where you have a low water content, and one where you have a high water content. And what actually happens, the blue, you could consider the blue as the membrane, basically, you see that in there are these kind of channels that are fundamental in the transport of H+ ions. So it means that this is a part of your membrane. If you are moving H+ ions, like this yellow dot here, it will move only through these channels, isn't it? So if you have a low water content, the hydrogen mobility will be quite low because it will have to move between very narrow channels and only along a few paths. Instead, if you have a high water content, you will see that the size of these channels will increase a lot because of the presence of water causing a swelling of your membrane, so a volume increase. And these large clusters of water will allow the proton to move very easily across the Nafion membrane. So, the net effect will be ionic conductivity in membrane low, because very difficult to go through this membrane. Ionic conductivity high, because you have a lot of highways for protons to move inside of this polymer. Now, the question is, how can I control the water content inside of the membrane? And that's the crucial point. Because the water you have inside of the membrane in equilibrium condition will depend on the atmosphere at which you are exposing it. So if I take now a very small piece of membrane and I put it here in open air, inside of here I guess we will have, 40% relative humidity. Okay? So, after a very long time, I can measure the water content of my membrane, and what I found is that I have more or less 3 molecules of water per each sulfonic group inside of my membrane. I then increase the relative humidity inside this room, we go to 100%, and then I wait a very long time. And what I see is that actually the equilibrium water content that I have in my membrane is much higher. Okay? So, the water I have in my membrane depends on what happens at the boundaries of my membrane. So, what relative humidity I have in the gases next to this membrane. If you perform this measurement in a laboratory, for sure, you find a curve like this. And you find that increasing the relative humidity, you increase the water content inside of your membrane, and there is a first part from 20 to 70% relative humidity, where the water content is still low. Then above 80% relative humidity, you see that there is a steep change in this water content. And this is because the morphology of the material has a transition from something similar to this to something similar to this very high water content level. And this thing is happening around 80% relative humidity. Okay?
This is happening for Nafion and aqueous membrane, like the data.
Yes, for sure. Depending on the material, this curve will change. The shape will be very similar. For sure, the absolute values will change. Okay. Okay. Then, once I have an equilibrium condition, okay, I can also measure the conductivity of the membrane. Okay. What I see in this case is that depending on the water content, I see an increase almost linear of the conductivity of the material with the membrane water content. So as much as I increase the water content, the higher will be the space available for ions to go through the membrane. And as you can imagine, this is linear with water content, but being water content not linear with relative humidity, you will see that conductivity depends in a kind of exponential way with relative humidity. Okay? Okay. Typical values of conductivity for a well-hydrated membrane is around 0.1 Siemens per centimeter divided centimeter, leading to an high-frequency resistance that goes between 10 to 15 million per square centimeter, depending on your membrane thickness. Okay, just to give some general numbers. Okay, so far things I think were quite easy, but when you are operating your fuel cells, this thing will become a mess. Because in real operation, you're not in equilibrium, okay? You're far from equilibrium because in the cathode catalyst layer, you're producing water, okay? Water is diffusing from one side to the other, depending on the water activity on the two sides of the membrane, okay? And also you have the so-called electrosmotic drag, which means that the proton moving through the membrane is bringing along also some water molecules. This happens because the proton does not move by itself, but in a kind of solvation state, so along with some other water molecules in some complex form, like for example H3O+. The point is that you have how much, and depending on how much current you are drawing, every proton going from anode to cathode is bringing back one molecule of water as a rule of thumb. Some molecules of water. And you are producing water at the cathode. So you have to carefully control water because the risk is that, okay, I take, because of electrosmotic drag, all the water away from the anode to the membrane. So on the anode side, the risk is that to have a dehydration of the membrane. So water is produced a lot on this side, goes through the membrane because of electrosmotic drag, but on this side you are missing water. If you miss water, ion cannot be transported, and so what you see is that there is basically your system does not work anymore. Okay, luckily you have the so-called back diffusion of water that will help you a lot. So you are producing water in here, you have a lot of water in the cathode side generally, and then you have this back diffusion of water because of different water concentration from the two sides that can more be used in order to manage the water from one side to the other. Now, this is, for example, a low Q density condition. Okay? Under low Q density condition, you are producing only a little amount of water, because the more current you go, the more water you produce, isn't it? So at low Q density, the water content across your membrane and in the catalyst layer could have a kind of profile like this. And will depend strongly on the relative humidity of the hydrogen on the anode side and the relative humidity of oxygen or air on the cathode side. You have a kind of equilibrium condition. You are producing a little water, obviously you have to stay in this stable condition for a long time, and in automotive maybe it's not what happens, but we could picture this in a stable condition as a kind of uniform water content in your membrane. And that's what happening in the low current density range. Instead, if you move to high current, what happens is that you are producing water at the cathode. So the water content at the cathode side increases a lot because you are producing water. Here you have a lot of water, maybe you also have some liquid water. So in this region, water content is extremely high. So, but on the other side, on the anode side, I'm not producing any water. So basically, the water content in here should not change that much. But instead, because of electroosmotic drag, I'm taking water from anode to cathode. And because of this, the water content decreases a little bit. This little bit depends on the operating condition, for sure. In the worst case, you could have this purple line going to 2 or 1 water content, making the system basically unstable. Okay. The other phenomenon that you see is that having a strong water content difference between the two sides, for sure you have a diffusion of water from one side to the other that will help you a lot in the management of the system. Okay. Basically, what we can conclude from this is that the conductivity of the membrane in the black case and in the purple case will be very different, okay? Because the average water content of the membrane is extremely different. So, we could assume that in this case, from low current density to high current density, the membrane resistance will not be constant anymore, and so the ohmic loss will not be a line anymore. But instead, it will have this strange shape, having a steeper increase at low current density, where the membrane could be kind of dehydrated, the black case. Instead, this loss gets mitigated at high current density because of water production, and so you deviate from this linear trend towards a lower ohmic loss. In your system because you are producing water in this part of the polarization curve, so the average conductivity of your membrane increases because of this mechanism. Okay? Okay, so we can study polymers in an equilibrium condition, but when we move to real operation, we get far from this equilibrium assumption, and what we see is that the water content depends a lot on the current density and the operating condition you are drawing. Then, to visualize the effect of membrane conductivity, the easiest thing is to change the membrane thickness, also in experimental life. If you want to evaluate how good is a membrane, you buy a membrane 10 micron thick, you buy a membrane 100 micron thick, you compare them, you get some information on the effect of this membrane, how good is this membrane in your system. And what you get is something like this. So when you increase the membrane thickness, basically, you are increasing the ohmic loss associated to this membrane. But differently from our simple model, we should have, according to a lumped model, basically a line which slope should double by doubling the thickness of the membrane. Instead, what we see is that there are significant changes also in the shape of this curve. And we see one very interesting aspect, that is, at a certain point, the conductivity of the membrane, this ohmic loss, tends to increase at certain Q density, tends to increase again, reaching a kind of limiting in the operation of the membrane. This happens because you are moving in a condition where all the water from the anode is drawn to the cathode side, and at the anode, even though at the cathode you have a lot of water, at the anode you have a very low water content, and so your conductivity is still increasing. And this is typical of thick membranes. You can find in the literature several papers on this. If you increase the thickness of the membrane, you observe that at high current density a kind of limitation in the operation because of the dehydration of the membrane. All the water from the anode side is pushed to the cathode side, and when you increase the thickness, the back diffusion becomes less relevant, because in a thick membrane, the gradient of water content is less steep. And so the back flux of water, because of back diffusion, is no more important. Okay. Going back to Earth, this means that when you increase the thickness of your membrane, you have this non-linear behavior of the ohmic loss inside of the membrane, that in the real world is very relevant. How this will affect our impedance spectrum? This is the simplest thing that you do in a lab when you test fuel cells. What you observe is that when your membrane gets dehydrated or has any problem or is too thick, you see that the high frequency resistance is very high. So, what we said before, this limit at high frequency of the spectrum, that is associated to the ohmic loss inside your membrane, inside your system, is strongly a good indicator whether you are dehydrating your system or not. This means that in all the fuel cell cars that are running all around, few of them, all of them, even though there are not that many, there is an EIS performed continuously in the stack to check the impedance in this point and to adjust the operating condition if the membrane resistance becomes high, indicating that the polymer is going through a dehydration. So you are continuously measuring this point here, and if you see an increase in this point, you reduce the flow, reduce the temperature, try to manage the relative humidity, increase the current, perform something, and you go back to the initial state. Okay, just a few words about the gas diffusion layer. The gas diffusion layer is an extremely tough topic. Most of the information of it are based on patents, actually, because it's a carbon cloth or carbon paper material, which properties depends a lot on the manufacturing technique. So if you have a proprietary manufacturing technique, you try to keep everything secret in order to avoid anybody in the world to copy your good material. But the key point about gas diffusion layer is that it is extremely complex to study from a scientific point of view. Because in our simplified view, the gas diffusion layer was characterized basically by one diffusivity. You know, DO2 was the diffusivity of oxygen inside the gas diffusion layer. But we did not care much in distinguishing the gas diffusion layer, the effect of gas diffusion layer and microporous layer. You remember the microporous layer? This thin layer that is put between the GDL and the catalyst layer in order to have a good electrical contact between the catalyst layer and the GDL, because electrons for sure must flow through the GDL. But unfortunately, the gas diffusion layer becomes extremely complex when we have to study the transport of liquid water. In fact, because of the fact that we are producing water at the cathode site, it could happen in some cases that part of this vapor condenses and you have formation of liquid water inside the GDL. For sure, this liquid water will block oxygen transport across the catalyst layer. And you will have a two-phase flow. That is probably one of the most difficult things in modeling on Earth. And if you couple it with an electrochemical reaction, you understand that now I do not have the time to discuss how to analyze mathematically this aspect. The key point is that in the polarization curve, the gas diffusion layer will affect the operation at high current density. That is extremely important because in this region you have very high power density, and in a car this means that you are here every time you have an acceleration. So this part is extremely important in a car. And you will see in the impedance spectrum that, as we said before, the GDL will affect mostly this feature at low frequency associated to mass transport limitations that you have inside the gas diffusion layer. Okay? So, basically, what happens when you have liquid water plugging? You have that oxygen, that is the green arrow, have to move counterflow with respect to liquid water that is trying to get out of your gas diffusion layer. Mathematically, I just introduced this parameter that is the liquid water saturation S, in case just you had to read some papers on this topic, in case you were interested. The liquid water saturation is a property inside the catalyst layer that tells you how much is the volume of liquid water divided the volume of the pores. Okay? So, saturation 1 means that all the pores are blocked with water. Saturation 0 means that there is no liquid water inside your pores. Okay. But this is just for a few of you that will have to care for this. Now, what you have in reality is that the oxygen diffusion coefficient will depend on how much liquid water you have in your system, so how much liquid saturation you have. And the reason why this is extremely tough to study is that it is no more a monodimensional problem. Because in a fuel cell, you have, this is a kind of clear drawing, I think. You have your catalyst layer here on the left, the microporous layer. And what happens is that you have your gas diffusion layer being in contact with the channel where the gas is flowing in some regions, and the rib. So, the metal or the graphite, where you have the electrical contact with the external circuit. So what happens is that under the channel, you can manage liquid water that can easily go through the gas diffusion layer and exit to the channel. But instead, under the rib, the water that is produced here tends to stay here because it has to travel through a very long path before going to the channel. And the region under the rib becomes flooded by liquid water. Now, the additional complication is that when you consider evaporation and condensation, you have also to take care of temperature management. So, it could be that since we have condensation in here, the temperature here will be higher. Here we have not, so we'll also have to match this problem of how much liquid water you have in your system also with the temperature distribution inside your system, making it a 3D extremely coupled problem. Also, numerical codes have a lot of problems in solving this kind of problem. But I just wanted to mention you, this is what happens in real world. Then I have just a couple of slides. The first one very briefly about the anode catalyst layer, because we are always neglecting anode catalyst layer in the lumped model, saying that the overpotential, so the loss associated to this component, is generally negligible. And that's what you typically find in the lab. Here, for example, you have some polarization curve taken from the literature. And you see how the polarization curve change when you reduce the platinum loading, how much platinum you put on the anode side, moving from 0.4 to 0.1, 0.05 milligram of platinum per square centimeter of cell. Okay? 1 milligram of platinum is still a lot, considering that the cost is around 20,000 euro per kilogram. Okay? So, actually, most of the cars running today have a platinum loading of 0.05, and you see in this case that there is no much difference between the three polarization curve. And people generally conclude that the anode catalyst layer has a minor impact in the potential loss compared to the cathode potential loss. So if you have to pay for platinum, put it in the cathode rather than in the anode, and try to keep this anode loading as low as possible. That's not true, actually, when you are working under very low relative humidity, because, as we saw before talking about the membrane, when you have a very low relative humidity, you have a low ionic conductivity, and since you are not producing water at the anode, one very severe problem at the anode side is dehydration. In the next lecture I will take, we will see, I will present some schemes of the typical vehicles, hydrogen vehicles. You will see how to manage this problem that is nowadays considered as. Now, I just conclude, after this long talk on detailed aspects of a fuel cell, this is a cross-section performed at the electron microscopy of the membrane electrode assembly that is used in the Toyota Mirai. Obviously, they try to keep everything as much secret as possible, but since now this car is considered old, because it dates back to 2015, now they decided to disclose part of the information. What is interesting in here is to see that they have this membrane that is a 10 micron. First of all, you know, electron microscopy, probably you don't know, this is a cross-section of the material. So you have taken your cell, you have done cut of this, you have put under vacuum with the electron, you try to have an imaging of this thing that looks like this. In the middle you see the cross-section of the membrane that is about 10 micron thick, which means that in automotive, typically you try to keep the membrane as thin as possible, as we saw in the previous slides, in order to have reduce the ohmic loss of the membrane and also to have a proper water management of the between anode and cathode. But when you have thin membrane, the problem is that they tend to break. You can form a hole inside of it. In order to avoid this, you put a layer in between based on PTFE that gives the mechanical strength to the membrane, making it possible to operate it with some pressure difference between the two sides. Okay? Then you have the two catalyst layers that are this thing. Because of the low magnification, you cannot see the pores of this catalyst layer. You see this is 20 micron, while the pores in the catalyst layer are in the order of 100 nanometers. So in this scale you cannot see it. But what you see in here, so you have what we said before, platinum and carbon and ionomer, and what they try to do is to keep the cathode catalyst layer and the anode catalyst layer the thinner as possible. In this case, 9 micron, that is quite low for the cathode, and 2.5 micron for the anode, that is extremely low. The reason is, if you try to keep the catalyst layer as thin as possible, all the transport phenomena across this layer will be mitigated, okay? Because if you have a thick catalyst layer, hydrogen ions or oxygen will have a problem to go through it. If you try to keep it as thin as possible, obviously oxygen activity will be homogeneous, the ionic potential will be homogeneous, and this is a good strategy to have very high performance and by working on the catalyst layer thickness. Obviously, when the thickness becomes too small, you will probably reducing the porosity of your medium or something else. So probably you do not have the ingredient necessarily to have it working. So there is an optimum in the catalyst layer thickness for sure. That depends on the materials you're using. Okay, here you have some numbers. This is a tin reinforced membrane, the cathode, with that you use in platinum cobalt, so not just platinum but an alloy, in order to promote oxygen reduction reaction. And the loading you see here is 0.3 milligram per square centimeter. At this step, at the anode, you have a lower loading, you have pure platinum, and the other thing that is not seen here is the gas diffusion layer that is 150 micron thick. So it is considered a kind of thin GDL, as well as we said before, in order to limit transport losses across the GDL, you try to reduce the thickness. But there is a strong interaction between your flow field, so the bipolar plate, and the GDL.
Excuse me, you told if there is a thin water layer, there will be, you said higher water content will go through large volume easily, ion conductivity will be more. But in case of thin membrane,
yes.
Won't it reduce?
In the case of the thin membranes, okay, like this one, for example, the water produced at the cathode will easily diffuse back to the anode. So you will have a water content that is more homogeneous across your catalyst layer and IQ in a condition where this sentence makes sense.
Okay. But you said the ion conductivity will be more if the membrane is like more thick or something like that.
No. The ionic conductivity depends on how much water you have in your membrane. The thickness tells you, for example, in a metal wire, the longer the cable, the higher the resistance. Not because it's changing the conductivity of the copper, but because it's changing the length of the cable. Okay. Okay. If you have any questions, I'm here. Otherwise, we meet next Wednesday, where we will talk about modeling. I will give you a MATLAB file to basically simulate the phenomena that we saw today. And then I will talk about the balance of plant and some information on how hydrogen cars work in the real world. Okay, bye.